We talked about how a positive plate, when we're dealing with a capacitor, will have a higher electric potential, and a negative plate will have a lower electric potential. And this then applies to batteries, where we talk about the potential difference or voltage, which is the change in electric potential between the high and the low. So if the high has a value, let's say, of 50, and the low has a value of 40, then the potential difference or voltage would be 10 volts. So this is going to apply then to batteries. A very simple battery would be something like if we have a box, and inside that we have an electrolyte, such as an acid like sulfuric acid, which is H2SO4, so sulfuric acid. And now we place two what we call electrodes. Now these will be two different metals, or perhaps one will be carbon. So we'll say that this electrode is carbon and this electrode is zinc. What's going to happen then is that the zinc is going to start to react with the sulfuric acid, and that the zinc will dissolve into sulfuric acid. When the zinc dissolves into sulfuric acid, it does so as an ion. So there will actually be a positive 2 charge on the ion that dissolves into sulfuric acid, leaving the electrode itself with an overall negative charge. So positive ions dissolve in the electrolyte, leaving a negative charge on the electrode. Now the part of the electrode that sticks out of the actual box is called a terminal. So the whole thing is called an electrode, but this little part that sticks out of it is called a terminal. Now the carbon is going to react with this, this slightly positive electrolyte now, because a positive ion dissolves and it has a slight positive charge. So the carbon reacts with it, and after the carbon reacts, it leaves a positive charge on the carbon's electrode. And again, so the terminal is the part that sticks out of that. These are called terminals. And so we have a positive and a negative terminal. This is similar to our positive and negative plate, so that this positive terminal has a higher electric potential, and the negative terminal has a lower potential. And so we can talk about its voltage, the difference between the positive and the negative. Now, as we stick a charge, such as the electron, within that field, the electron is going to move towards the higher electric potential. But where is the electron in this situation? Well, unfortunately, a lot of times people think that a battery is really just a big box of electrons. That's not the case. The electrons are already in whatever it is that you're hooking up to your battery. So let's say you hook up a light bulb to your battery. The electrons are already in the light bulb. Everything's made up of protons, neutrons, and electrons. So the electrons are already there within the filament. By connecting this to our battery, we just get those electrons to start to move towards the higher electric potential. They're moving towards the positive terminal. So again, the battery here is just making a positive and negative, and then we talk about the potential difference or the voltage between the positive and the negative, in this case what we call terminals. We've had a lot of different words here floating around that sound very similar to one another. And so I also want to talk about how to keep track of the different things that we've talked about. For instance, we've talked about force, and then we've talked about fields. And I'm going to drop the words that sound similar, like electric. We've talked about potential energy. And we've talked about now this electric potential. There's no way around it. Both words are used over and over again. So the electric potential. And so we look at their equations that we've been using. And the electric force, the force, is KQ1 Q2 over R squared. That's measured in newtons. The field is KQ over R squared, and it's measured in newtons per coulomb. And these two values are vectors. Now these equations, I said, do not include the negative charges. Instead, being vectors, we're going to add a direction at the end. So leave off the negatives and then add a direction at the end. These two things here, the potential energy is KQ1, Q2 over R, and it's measured in joules. And now this electric potential is KQ over R, and it's measured in volts. And these two things are scalars. Now in these here, we have to include the direction, or the negatives. So we must include negative charges. And this has no direction. So when we add them up, we just add them up without having to break them into any components. Now the similarities we see that in force and potential energy, they're both KQ1, Q2 over. Here we're just dropping the square. So when we move over to scalars, all we do is drop the square. And so if it only adds over R, we include the negatives and we do not have a direction associated with it. If there's an R squared on it, we are vectors and we do not put the negative charges in our equations. We just leave everything as positive. And we must include a direction whenever we write our answer. So hopefully this chart here will help you to remember what to do and which equation refers to which. We have electric force and electric field are vectors, and potential energy and electric potential are scalars.